Let's evaluate these 4 definite integrals using the fundamental theorem of calculus part 2. In fact, if I was just told to evaluate these definite integrals or just told to integrate, my approach would be to use the fundamental theorem of calculus part 2 because it's going to be the easiest way. I could use Riemann sums for this one. I don't know that I'd want to for these ones. I could get area approximations for any of them, but the fundamental theorem of calculus part 2 gives me a very easy way of evaluating these, provided I can think of an easy antiderivative. This first problem, the definite integral from 0 to 2 of 4 minus x squared dx, was actually the very first area problem we considered. Way back in section 5.1, we approximated the area under the curve 4 minus x squared using an upper sum with n equals 2 and 4, lower sums with n equals 2 and 4, and a midpoint rule approximation. In a later video, we even found the exact area by taking the limit of a Riemann sum, so we know the exact area is 5.3 repeating, 5 1/3, or 16 thirds. In this video, because I can easily find an antiderivative for 4 minus x squared, the antiderivative of 4 is 4x, the antiderivative of x squared is 1/3 x cubed, and I need to evaluate that from 0 to 2. Remembering this shorthand notation that says I'm going to plug in 2 and get a value, and then take away what happens when I plug in 0. Well, when I plug in the 2, I get 8 minus 8 thirds, and then plug in the 0, and well, I get 0, and that's not too interesting. 8 minus 8 thirds, well, that's 24 thirds minus 8 thirds is 16 thirds. And I've found that exact area under that curve by this definite integral, but this time kind of the easiest way we can using the fundamental theorem of calculus part 2. Now I'm asked to integrate from 0 to pi of sine x. So I need an antiderivative for sine x. And the antiderivative of sine x is minus cosine x, evaluated from 0 to pi. Well, the cosine pi is minus 1, so I have the opposite of minus 1 is 1 minus the cosine of 0 is 1, so the opposite of that is minus 1. 1 and 1 make 2. Well, if I think about the graph of sine, I now know that on the interval from 0 to pi, the exact area under that curve is 2 units. And if I remember correctly, that came up in a previous video, and now we know it for sure. All right, 2 more examples in this video. I need an antiderivative for 1 over x squared plus 1. Well, 1 over x squared plus 1 is the derivative of inverse tangent. So that makes inverse tangent my antiderivative. The inverse tangent of 1 is pi fourths. And the inverse tangent of 0 is 0. So I've evaluated my definite integral with just one example to go. I was asked to integrate from 1 to 3 of t squared plus t minus 3 all over t dt. And this example's here just to remind us that sometimes it's easier to do everything we do if we do some algebra first. T squared over t is t plus 1 minus 3 over t. I need to find an antiderivative, 1/2 t squared plus t minus 3 times the natural log of the absolute value of t from 1 to 3. Now in this example, I don't really need to write the absolute value here because I'm on the interval from 1 to 3 where natural log is positive or 0. But I was like reminding myself that the most general antiderivative would have that absolute value in it. All right, I need to plug in a 3. So I get 9 over 2 plus 3 minus 3 times the natural log of 3. Minus, plug in a 1, 1/2 plus 1 minus 3 times the natural log of 1. The natural log of 1 is 0. All right, well, so now I just need to write down the most simple answer I can. 9 over 2 minus 1/2 would be 8 over 2 is 4. 3 minus 1 would give me 2. And I still have that minus 3, the natural log of 3, which is 6 minus 3 times the natural log of 3. And that's the exact value of my definite integral. But if I wanted to approximate it to one decimal place, I would find it to be about 2.7.